Hi, and welcome to this presentation. My name is Eline de Grieze and I work together with Gilles Castel and Pieter-Jan Thijs. There are tough problems in mathematics people are trying to solve for many years, and eventually they are solved with a complicated and long proof. Often, many different techniques and deep results are included. One example of this is the Riemann hypothesis, which was already discussed in another presentation. Nevertheless, sometimes these challenging questions only require a new perspective, a link nobody thought of, but that made an elegant and understandable solution possible. This talk will be about such kind of a problem, namely the sensitivity conjecture. We will discuss a relatively old problem in computer science that was proven last year, and we will have a look at that proof. In this tweet, we can see a summary of the proof, which is enough for experts. Even for people not acquainted with the subject, the longer proof is not very hard to understand and is only 2 pages long. At the end of this presentation, you will hopefully understand the tweet. This simplicity shook the world of computer science. Let me first introduce Hao Huan, as he is the central person in our talk. He is 33 years old and he was born in China, and he left his hometown at age 14 to go to high school. Subsequently, he started his major in mathematics in Peking University, but finished this at UCLA, Los Angeles. He also obtained his PhD there. He has been a postdoctoral fellow at Princeton University, and currently he is an assistant professor at Emory University. He is a member of the research group Discrete Mathematics and Theoretical Computer Science, which belongs to the Department of Mathematics and not the Department of Computer Science. His main research interests are extremal combinatorics and structural graph theory. If you are not impressed yet, we mention his Erdős number is 2. We will have a look at the problem and its context, even though a complete overview of everyone who has made an attempt is pretty much impossible. It is like a who's who of discrete mathematics and computer science, as Scott Aronson, a computer scientist at Texas University, says. Furthermore, Pieter-Jan will introduce some building blocks for the proof, followed by the proof itself, presented by Gilles. Pieter-Jan will also conclude the presentation. A central notion in computer science is Boolean functions. The input for such a function f is a string of n zeros and ones. This transforms in a single output bit, which can be interpreted as true or false. For example, the function AND returns 1 if the input string only consists of ones, and 0 otherwise. In a real-life situation, the input string can be constructed as answers to yes or no questions. For instance, if you are asking for a bank loan. The outcome of the function then represents whether you get a loan or not. Moreover, logic circuits use these functions as well. For computer science, the complexity of these functions is very important, as they appear everywhere. The aim is to understand how much computation is necessary and sufficient to perform certain computational tasks. This is difficult, and therefore a variety of simpler and more limited models of computation have been studied. Some of them give interesting insights for the time or space needed to compute a function. The most important one is decision tree complexity, which we will not talk about in this presentation. Nevertheless, sensitivity, which is central in our project, gives a lower bound for the time needed by a parallel RAM to compute a function f, and thus it is important too. There are many different complexity measures, and pretty much all of them are polynomially related. In a sense, you can look for a measure that is easy to compute, and discover nice bounds on measures that give more insights for time or space. The importance of the polynomial relations is that a polynomial complexity is known to be doable, whereas an exponential one requires small input strings. If the length of the input string then increases, the extra computation time can be huge. You can see some examples on the slide. The only exception of polynomial relation seems to be for block sensitivity and sensitivity, in that order. The sensitivity conjecture briefly says that the sensitivities do belong to that bigger framework, and that they are interrelated as well. This is what we are trying to solve during this presentation. A first step in understanding the conjecture is to look at some basic definitions. We start with local sensitivity. We are interested in how the information of the string determines the output. How many bits have the property that if we change them, the outcome changes as well. For instance, for the bank loan, a different answer on the question, "Do you have a job?" could change the decision of the bank. We denote this by the string x, superscript the set of indices that we flip. For local sensitivity, we restrict ourselves to singletons. On the slide, we present an example. Our input string contains 3 bits, blue being 0 and red represents 1. The Boolean function we use is x or y and z. When we change the first bit, x or y is true instead of false, and the outcome will change. We say that f is sensitive to the first bit. The same happens for the second bit. Flipping the third bit does not have an influence. In total, there are 2 bits f is sensitive to, so the local sensitivity of the function for the input string is 2. Remark that we fix the input string throughout this process. That is generalized in the notion of global sensitivity, or sensitivity in short. We take the maximum of the local sensitivities over all possible input strings. In this case, that is 2 as well. We can represent all possible input strings on an n-dimensional cube, where n is the length of the string as usual. For instance, for n is 3, the coordinates yield indeed the possibilities. We color the point according to the outcome, blue for 0 and red for 1. This visualization has an interesting property. Fix an input string, or thus a vertex. Whenever you take a string which differs at exactly 1 bit, it is contained in the same edge of the cube. This can be seen as an indication for a relation with sensitivity, where we also flip 1 bit at a time. In the sensitivity conjecture, we compare sensitivity with block sensitivity. We used to flip the bits one by one. For block sensitivity, as the word says, we are allowed to flip blocks, multiple bits at the same time. Again, in the definition, we work with the indices and we indicate which ones we flip. The blocks have to be disjoint though. In contrary to what may be expected, the blocks do not have to be connected. The first bit, together with the third one, is for instance a block. There is again a local version, where the input string is fixed, and there is a global version that is the maximum of the local one over all possible input strings. As sensitivity is equivalent to block sensitivity with singleton blocks, we have that S of f is less than or equal to the block sensitivity of f. In our example of f as x or y and z, you can easily compute that the local sensitivity for this input string is 0. Nevertheless, as we see here, when changing 2 input bits at the same time, the outcome does change. There are multiple options to do this, but not in a disjoint manner. You can see an overview of the possible blocks one can combine on the slides. The local block sensitivity is then 1. We have now discussed sensitivity and block sensitivity, 2 important complexity measures for Boolean functions. Another one we will use in the proof is the degree. You can represent Boolean functions as real polynomials. For instance, when you take the OR function for x and y, you get the following polynomial. We can fill in values for x and y, being true or false, and then indeed the polynomial agrees with the logical expression. The degree of this polynomial is then the degree of the Boolean function as a complexity measure. You can also reduce more difficult examples to the easier ones. For instance, for the Boolean function we already used, x or y and z, you can implement the polynomials piecewise, and then you can use distributivity. As I already mentioned, the sensitivity conjecture is pretty old, almost 30 years now. Officially, this was conjectured in 1994 by Nissan and Chegedi, but that was the official publication date. It was known earlier, from 1992. Important milestones include Chunk's article of 1988, which gives a first lower bound that Hung later improves in his central theorem that Gilles will discuss. Gotsman and Lineal's equivalence dates from 1992 and was crucial as well, as we will illustrate. Furthermore, in 1994, Nissan and Tegedy didn't only raise the question from the conjecture, but they have shown similar results for other complexity measures too, and they did an attempt for sensitivity. During the years that followed, many little contributions have been made, but none of them are still of great importance. In June 2019, the conjecture was finally proven by Hao Huang of Emory University. As already mentioned, all common complexity measures are polynomially related. The question of the sensitivity conjecture is whether this is also the case for sensitivity and block sensitivity. To be proving this, we need to be acquainted with some fundamental principles, but Pieter-Jan will guide you through this.
Thank you, Eline. Before we can start to prove, we first need to take a small detour in the world of graph theory. As you might know, a graph is in fact a couple. The first component is a set of vertices, here labeled from 1 to 6. The second component is then a set of edges, which are the white lines connecting these vertices. To such a graph, we can also associate an adjacency matrix. Such a matrix is made up of zeros, shown in black, and ones, shown in white. For example, take the element on the second row and the first column. This is a white element, which means that the corresponding first vertex and second vertex will be connected by an edge, as you can see on the figure. In particular, note this matrix is symmetric, which is something we'll need later on in our proof. The property that we will be interested in is the degree of a graph. First, the degree of a vertex is the amount of other vertices that are connected to it by an edge. In this case, for example, vertex 2 has in fact degree 3. One can also read this degree from the adjacency matrix. It is obtained by summing all the elements in the corresponding row or corresponding column. We then define the degree of a graph, where the degree is symbolized by a capital delta, to be the maximum of the degrees of all the different vertices. The last concept we'll need is a concept of a subgraph. To obtain a subgraph, one takes an existing graph and then removes one or more vertices and maybe also some edges as well. In this case, we remove vertex 6 and of course all its corresponding edges. We then obtain an induced subgraph, which will commonly be denoted by the symbol of a subset. Because we changed the graph itself, we also need to update the adjacency matrix. In this case, we need to remove row 6 and column 6. First, note that it is purely accidental that these are the last row and last column. For example, if we would have removed vertex 3, we would have needed to remove row 3 and column 3. The matrix we then obtain is called a principal submatrix. Furthermore, it is possible to extend this by removing multiple vertices at the same time, as long as one removes the corresponding columns and rows as well. However, we won't just need any type of graphs. In particular, we'll look at a very specific type of graphs, which are called bit cubes. Such a bit cube is not new. You've already seen one when Eline talked to you about sensitivity. On the right, we formally define what such a bit cube should be. A bit cube, say Qn, is in fact a graph where the vertices are n bits and tuples of bits. This means that the total amount of vertices will be 2 to the power n, which is simply all the possible combinations of n bits. We then define that such vertices should share an edge if they have exactly one bit that is different. For example, suppose that the different bit is the first bit. This then leaves 2 to the power n minus 1 combinations for all the other bits. Of course, this needn't be the first bit or the second bit. It can be any of those n bits. This means that to get the total amount of edges, we need to multiply this amount by n. The last concept we'll need is the concept of building a large bit cube from several smaller ones. Here on the right, we have a one-dimensional bit cube and its adjacency matrix on the left. In particular, the bit cube contains a 0 bit on the left and a 1 bit on the right. Of course, they differ by exactly 1 bit, so they need to be connected by an edge shown in white. For our construction, we first duplicate this one-dimensional bit cube. Then we connect the corresponding vertices. In particular, pay attention to the geometrical structure of this construction. We take the first bit of the lower bit cube and connect it with the first bit, or better vertex, of the upper bit cube. Also, we take the second vertex of the lower bit cube and connect it with the second vertex of the upper bit cube. This means that in the adjacency matrix, in the second and third block, we get the identity matrix. We now repeat this process a couple of more times. First, we duplicate the square, and then we connect the corresponding vertices. Because we only connect the corresponding vertices, this means that in the adjacency matrix, we again get the identity matrix in the second and third block. We can repeat this process a couple of more times to get actually quite nice looking figures. In particular, it is the special structure of this adjacency matrix what will allow us to prove the sensitivity conjecture. To start the proof, we first list some known results. At the top, recall the sensitivity conjecture. It says that there should exist a constant c, such that for every Boolean function, we have that its block sensitivity is denominated by its sensitivity to the power c. First, there is a lower bound which relates block sensitivity to degree, which Eline also introduced to you earlier. The original version was proven by Nissan and Segedi in 1994, but it contained a factor 2. Later on, this was improved by Tal in 2013 to the version you see here. However, this is a slight inconvenience. It relates block sensitivity to degree. This means that we now need to relate degree to sensitivity. For this, we have an equivalence formulated by Gotsman and Leniel in 1992. To suppose first that there exists a monotone function h. Then, evaluating this function in the degree will be smaller than the sensitivity only and if only an equivalent statement is true about induced subgraphs. Now, to prove the sensitivity conjecture, it only remains to prove this last equivalent statement. Furthermore, note that we don't need any monotone function. As showed, the square root function will be sufficient. At the bottom, we now have the final theorem we need to prove. This will be done in a series of 3 quick lemmas and will be presented to you by Gilles.
Thanks, Pieter-Jan. I am Gilles Castel, and I'm pleased to present to you the proof of Horn on the sensitivity conjecture. This proof starts off with 3 lemmas. In the first lemma, Horn constructs a signed graph, which is a graph where each edge has been assigned a sign. The construction goes similar as the one Pieter-Jan showed you before, but in each copying phase we invert the signs of the edges. So here we start off with a one-dimensional bit cube where all the edges have sign +1, denoted in white, and then we copy this graph and we invert the signs. Here -1 is denoted in green. Finally, we add identity matrices on the off-diagonal, and we repeat this process. In this way, we get a signed bit cube with its signed adjacency matrix on the left. And lemma 1 tells us something about the eigenvalues of this matrix. Formula-wise, this looks as follows. We start off with a 2x2 off-diagonal matrix, and then we construct AN inductively. We place the previous step on the upper left, and once negated in the lower right. Finally, we add identity matrices on the off-diagonals. And lemma 1 says that half of the eigenvalues of AN are square root of n, and the other half are negative square root of n. And the proof uses a little trick. So first we prove that AN squares to n times the identity. And we do this by induction. So the base step is simply squaring A1, and by basic matrix multiplication, we get that this is 1 times the identity. And then the induction step uses block multiplication of matrices. So we first rewrite AN using this definition, and then multiplying, we get on the upper left AN minus 1 squared plus I, and using our induction hypothesis, we find that this is equal to n times the identity. On the upper right, we find the following. and after simplifying the identity matrices, we find that these two terms cancel, leaving us with 0. Repeating the same steps for the lower half of the matrix, we can see that indeed an squared is n times the identity. This means that the eigenvalues of n are positive or negative square root of n. And now the final trick. The trace of an is 0. And this means then that half of the eigenvalues are square root of n and the other half is negative square root of n. And this concludes the first lemma. The second lemma is a well-known result. It's called Cauchy's interlace theorem. It states the following. So let A be a symmetric matrix and let B be the matrix obtained by removing the last row and column of A. Then the eigenvalues of B interlace those of A, as you can see here. We won't prove this in this presentation. It is widely known, and its proof would lead us too far. However, we will give an example to get a feel of the power of the theorem, especially when we apply it multiple times. So have a look at this randomly chosen matrix. We plotted its eigenvalues on the right. And now we remove the last row and column, and the theorem says that the eigenvalues should be interlacing, which looks like this. Now repeating this process, you can see the structure that emerges, and this structure will be important later. It should also be noted that this works not only if we remove the last row and column, but this works for any principal submatrix we obtain when removing a corresponding row and column. Now we are ready to discuss the final lemma. This lemma also involves a standard resulting graph theory, but this time with a twist. It states the following. So let H be a graph and A be a matrix with entries n -1, 0, and 1, such that the absolute value of A, taking entry-wise, is the adjacency matrix of our graph H. So this is saying that A is the adjacency matrix of H up to sides. And an example of such a matrix is the matrix we constructed in lemma 1, which was the adjacency matrix of a bit cube up to sides. So now, given such a matrix A and a graph H, the lemma claims that the maximum degree of the graph is greater than or equal to the biggest eigenvalue of A. This would have been a standard resulting graph theory, were it not for the fact that A can also have -1s as entries, and this is the twist. So the proof, however, is very similar to the proof of the standard result. So let V be the corresponding eigenvector, and Vk be the component of V which has maximum absolute value. Then we have that lambda 1v is the same as AV, and now considering the absolute value of the kth component of these vectors, we obtain the following. Now we write out the matrix product as a sum, and we use the triangle inequality to move the absolute value signs inside the sum. Now, note that on the left hand side we have Vk, and on the right we have Vj, and we would like to cancel these terms. And to do this, we can replace Vj with Vk, and the inequality still holds. This is because Vk is the component of V which has maximum absolute value. So now we can cancel the Vk's, and we are left with the following. But what is the right hand side? It's a sum of entries and the column of A, up to sides of course. And this counts how many edges in a graph are connected to this column, so to say. So it's the degree of a vertex, the vertex corresponding to column K in this case. And an upper bound for this is of course the maximum degree of our graph. And then the final thing left to do is to remove the absolute value signs around lambda, and we are done. This concludes the last lemma. So, as a quick recap, on lemma 1 we constructed a matrix which was a signed adjacency matrix of a bit cube, and we also calculated its eigenvalues. In lemma 2 we discussed the interlacing theorem of Cauchy, and in the last lemma we proved an inequality involving the maximum degree and the largest eigenvalue of a signed adjacency matrix. And now we are ready for the proof. Let us remind ourselves of what we are trying to prove. Let H be a subgraph of an n-dimensional bit cube, which is induced by more than half of the number of vertices. Then the maximum degree of H is greater than or equal to the square root of n. First consider the signed bit cube with its adjacency matrix An, as we constructed before. Because H is a subgraph of our bit cube, it induces the principal submatrix of An. So for example, on the top you have a bit cube with its adjacency matrix, and on the bottom you have its signed cousin. Now, consider a subgraph of this bit cube, induced by more than half of the vertices. In this case we have 5. Then its adjacency matrix is obtained by removing 3 rows and columns from the original matrix. Now doing the same in the signed version, you obtain a principal submatrix B of A, which is up 2 signs the adjacency matrix of our graph. Now, what about the eigenvalues of B? B is obtained by removing rows and columns, so we can use Cauchy's inverse theorem and we get the following picture. So the eigenvalues of A are square root of n and minus square root of n, as illustrated here. We spread them out a bit to make the figure more clear. Upon removing one row and column, we see that the number of eigenvalues which are square root of n drops by 1. Repeating this process, each time the number drops by 1, but we can still be assured that the largest eigenvalue is square root of n, as long as we don't remove too many columns. But as B is obtained by removing less than half of the rows and columns, and we started with half of the eigenvalues being square root of n, we find that the biggest eigenvalue of B is still square root of n. And when we would have removed one row and column more, we see that this can't be guaranteed anymore. So, the only thing left we haven't used is lemma 3. And this lemma says that the maximum degree of H can be estimated by the biggest eigenvalue of B. So finally we find that the maximum degree of H is greater than or equal square root of n. And this concludes the proof. So what is the essence of this proof? Well, it's really based on a well-known inequality in graph theory, connecting the degree of a graph with eigenvalues of its adjacency matrix. However, we added a twist. We also allowed for negative ones, and in some sense we let the problem breathe a bit more. By allowing negative ones, the eigenvalues of the matrices we're considering became very structured. They were all square root of n or negative square root of n. And because these eigenvalues were so close to each other, they really constrained the eigenvalues of submatrices, which in the end provided a very tight bind for a problem. With this concluding remark, I hand over the mic, or better the screen, to Pieter-Jan.
Thank you, Gilles. At the start of this presentation, we promised to you that we could prove the sensitivity conjecture in a single tweet. Now that you've seen all the technical details of the proof, we can return to this very tweet. The first paragraph refers to the first lemma that was presented to you by Gilles. It claims that we can construct a bit cube in such a way that the edge-signed adjacency matrix has the property that exactly half of the eigenvalues are plus square root of n and the other half are minus square root of n. We then introduce a second lemma, which is based on Cauchy's interlace theorem. It claims that any induced subgraph of such a bit cube, provided we do not remove too much vertices, has a property that its maximum eigenvalue is still greater than this square root of n. Finally, in the third and last lemma, we relate this maximum eigenvalue to the degree of a graph. And hence, the sensitivity conjecture is proven. However, we also said that this proof would be sufficient for experts. As this is the first time you've seen this proof, we'll quickly walk you through the remaining steps. At the top, we have the statement we just proved in the tweet. We then recall the equivalence formulated by Gottman and Lineal in 1992. We seek a relation between degree and sensitivity, and it gives such a relation only and if only an equivalent statement about induced subgraphs is true. However, this statement appears slightly different than what we've proven in the tweet. Indeed, it talks about any induced subgraph except those with exactly half of the eigenvalues removed. Luckily, this isn't a problem. It is for this reason that we introduce the maximum. If we remove less than half of the vertices, we exactly have the statement that was proven in the tweet. However, if we remove more than half of the vertices, the statement is still satisfied by looking at the maximum. For this, we will need the complementary graph, which is simply the bit cube minus all the vertices and edges of the induced subgraph. Now that this statement is true, we know that the degree of a Boolean function should always be smaller than its sensitivity squared. We can combine this with a lower bound we already mentioned before. Nestor and Cesuri proved such a lower bound in 1994, and Thal later improved this to the version you see here. When we then chain these two inequalities, we have proven the sensitivity conjecture, namely block sensitivity of a Boolean function should always be smaller than its sensitivity to the power 4. So, in this presentation, we introduced you to the world of Boolean functions. We talked about sensitivity, about block sensitivity, and also some other complexity measures. It turns out that all of these, including block sensitivity, are polynomially related. Except for sensitivity, this was not proven yet. In the end, it has taken almost 30 years of research before we could finally confirm this suspicion. For a long time, no breakthrough has been made until one finally proved the sensitivity conjecture in 2019. Now that you've seen the proof, you might think, well, it's not that difficult, right? Well, it still took them 30 years. And I also have a statement from Wang in which he looks back on the years in which he worked on this theorem. He said that he revisited this conjecture every time when he learned a new tool, without any success. But at least thinking about it helped him fall quickly asleep during many nights. I guess for some of you this might be quite relatable. Now, in our eyes, the real takeaway of this conjecture is not the result itself. It is also about the proof that is in fact quite short and surprisingly elegant. And that was achieved by ingeniously combining tools from various areas of mathematics at the same time. And thus, to all of you, it may be a reminder to make sure you two are well aware of other related areas of mathematics. Maybe they might help you with your current work as well. We thank you for listening to our presentation.